packet here. Any questions? Pages 11 through 14. Okay, so today we're going to see how much we can get through 15 through 18. Okay, so let me read through 15 and then have you guys try it, and then I'll walk through it. Okay. All right, so consider differential equation dy dt equals 3 minus y cosine x. Let y equals f of x be the particular solution to the differential equation. F of 0 equals 1. There's this initial condition, f of 0 equals 1. The function f is defined for all real numbers. A portion of the slope field is given below. Sketch the solution curve through the point 0, 1. This will be the easiest type of problem where all you need to do is to identify a point that they're talking about, and then just follow the path of the graph, follow the flow, and sketch your graph. So it really is as easy as it seems. Part B, write an equation for the tangent line. So order pair, slope. Your slope comes from your derivative. I would use this space for part B so that we can save that part C for all the work that we're going to do with separating variables and all that. So go ahead and try part B, and I'll work alongside you guys. So we know that linear approximation is just going to give us an approximation of the actual point on the curve. So y of 0.2 is equal to 1.4, and we know 1.4 is some approximation of the actual point on the f graph at 0.2. So I use this quickly line here. Okay, part C, find a particular solution to the differential equation with initial condition 0, 1. So we're gonna go through our steps here, right? Get our fractions to show up, cross multiply, separate our variables. X is on the right, Y is on the left. See if we can go through those steps. All right, go ahead and try those steps, and I'll follow up with my steps too. Okay. dy dx's are in their final places. One thing is out of place. What's out of place? 3 minus y, right? We got to move that where? Left side in the denominator, yeah. Okay, y's are together, x's are together. What would your next step be here to go through our integral process? Yep, your u value being more than that, 3 minus y, yeah, the entire denominator, right? The hope is that this will eventually turn into a 1 over u du. We do want to go through your substitution because that negative y will produce a negative 1 derivative. So there is going to be something to keep track of there, right? Oh, and something to keep in mind also, the whole point of u substitution is that you want to take a complicated problem and kind of produce or create an easier problem out of it. So if you do u substitution, it's never going to be a 1-for-1 substitution, right? It's never going to be u equals x or u equals w. It's always going to be more than that. So if you're doing a 1-for-1 substitution, you might as well not even do u substitution because you're just changing the variable and the problem is not going to look any different. It's not going to look any simpler. So yes,
you could still work, but it wouldn't be
right. It can still work, but it's, you're just creating additional work where you're not making much progress. But yes, if it's one variable, you can make a 1-for-1 u substitution. But I might as well just jump into either power rule or natural log. Okay, so all this is for the left side here. U equals 3 minus y. Derivative is -1. Make my substitution. I have 1 over u du. Pull the -1 out in front. 1 over u is natural log. The negative is going to have to stay because of the derivative that came from 3 minus y. And then replace the u back in terms of y. And then we can work on the right side. Now, right side should be pretty easy. What's the integral of cosine? Just sine, yeah. Let me reset at the top here. right, so we're done with the calculus. Now we have two things left to do. Find a way to solve for y, find a way to solve for c. I want to decide that I want to solve for y first. I figure that solving for c might be a little messy with that natural log in the way, so maybe I want to get rid of that natural log first. But before I can involve getting that natural log out of the way, what do you think could be a good first thing to do? Yeah, let's take care of that. What can we do with this negative here? Yeah, let's distribute that through, right? We want to involve e in natural log, but that negative is kind of messing with that relationship there. So if we can just multiply everything through by -1, get that negative to shift over to the other side, and that way that left side is a little bit cleaner for us to involve that base e. Okay, so now that left side is a little bit cleaner. E in natural log. Cancel each other either other out. Split this up, e to negative sine x, what? Plus c. How can I separate this out to make it so that I can get that c away from this expression? Times what? Times e to the c. So the rule that a to the m plus n is a to the m times a to the n. So that exponent addition is going to turn to multiplication at the base level. Turn that e to the c is to just be one big c, drop the absolute value. I'm just moving things around a little bit differently so I can get that y to be positive. So y is equal to 3 minus c e to the negative sine of x. Okay, so I'm going to say my last thing to solve is c. Okay. What order pair can I use to help me get that c value? 0. I'm sorry? -2. Yeah, so I moved some things around here. I skipped a step here. Yeah, it would be -2, but it's -2 equals negative c, and I just multiply both sides by -1. Okay. Okay, let's go ahead and try page 16. You'll do fill in 6 points using or building the slope, a sketch a slope field with 6 points. Let me just kind of remind you a couple of things here. What if I get a slope of 0/4? How would you represent that on the slope field? Horizontal line. Okay. What if I had 9/0? How would you represent that? Leave it blank. Good. Leave blank. Some students want to do a vertical line, but that will be incorrect. So you'll leave it blank. So we'll find the order pair here. This is 0, 2. Plug into the derivative, and then whatever number you get, you just interpret that as best as you can. If you get a negative number, then just represent with the negative slope. Here, if I plug in 0, 0, I'll get 0/-1. That's a slope 0. So I do want to represent that with a horizontal line. 2, 0, horizontal line. Positive slope, steeper positive slope. Okay, so B and C should feel very familiar from the previous part. You're going to build your tangent line equation and then plug in the decimal to do linear approximation. And then part C, solving your differential equation. Okay, so try those parts. Very similar to last week. Pretty much, yeah. The integral rules may be different once you set up your differential equation, but yeah, virtually identical steps in terms of process. Say it again.
How should you get like the 3.9?
3.9. So I did 9 times 0.1. And then plus 3. So this is my argument with tangent equation. We're just taking the decimal 2.1, inserting for the x, and getting the decimal value. Linear approximation. We like to have that dy on the left side, dx on the right side. But we see that we have things that are out of place on both sides, so we'll make a double division here. Both the x minus 1 and the y squared will swap places, and they're both going to end up in the denominator of the other side. So we can get full separation, right? We want all the y's on the left, all the x's on the right. Okay, we have full separation, so we're ready to involve our integral process. Can we talk about what rule that we want to use on each side, though? How would you handle the left side? Power rule, right? Bring that y to the top. How about the right side?
U substitution.
U value being
X
minus 1. Yeah. So this will eventually end up being 1 over u du, because this will be a u to the first power, right? Okay. Okay, so here's the result of my left side. Here's the result of my right side. We'll set them equal to each other. The plus c will show up, and then we can begin thinking about how we can solve for c and solve for y.
How does that turn into -1 over y? I still don't like how to ever get out of that.
So we know the y has to come down, right?
Because
The negative exponent. I just decided that I want to do it now because eventually it's just easier for me to think in terms of an exponent that's positive. So that's why I moved it down.
Okay.
And the negative can be either top or bottom. So I just moved it to the top. Okay, everybody okay here up to this stage where we're done with the calculus and we're just down to the algebra. So you can solve for y first. You can solve for c first. I think I decided that going ahead and solve for c feels a little bit easier before the messy fraction that's going to come up after I flip both sides. So that's kind of like just my thinking that maybe it's a little bit easier to solve for c before all the messier fraction comes up. So I'm going to just go ahead and plug. Now, if you decide to solve for y first, it's not wrong. I mean, I think it's just a matter of what you think is easier. I'm gonna treat it like I think it's easier to solve for c here, but I think it's just a
Depending on the problem.
yeah, depends on the problem. There's no right or wrong. The advantage of this is that natural log of 1 is 0, so that's easy to resolve. I can just solve. I can say c is just equal to negative 1/3. Okay, so now I can focus on what may be a little messy or trying to get that y by itself. The first thing I see is, well, there's two things I want to do. I want to get that negative away from the left side. And second, I know I got to flip that y to the top. So I'll do the easier one first. I'll take care of that negative. Multiply everything through by -1. Okay, so I do want to talk about something here. Maybe you're thinking, oh, if I just flip everything, then I can get y by itself. But there's a certain way we've got to do it. We can't say, oh, this becomes y. This becomes 1 over natural log of x minus 1. This becomes 3 over 1. Okay, we can't flip the fractions individually if there's a plus or minus in between. So this is what I would do. I would write it this way. I know it's messy. You got that, but this is the algebraically the more correct way to do it. Okay. It doesn't matter how messy it is, as long as you can get y by itself. So I'm going to just flip both sides here. Now I have fraction equaling a fraction. Now a much cleaner relationship here. I can flip the numerator denominator. I can flip the numerator denominator. It's the same thing as cross multiplying and then solving for y, but this kind of feels a little bit quicker here. Whatever I do to the left side, I can do to the right side. I just can't flip them individually. Then I'm breaking some algebraic rules there, but I can flip the whole thing to the denominator. So don't worry about, when you're solving a differential equation, don't worry about how messy your right side is. As long as you're following algebraic rules, as long as you get that y by itself, whatever mess is on the right side, as long as it's equivalent to a simplified version, that's good enough. College Board graders will accept that. This is not necessary, or this is not, but sometimes I feel like some students feel that, oh, they want to just kind of have that extra assurance, whether this is correct. One way to kind of test that assurance, it's not guaranteed to mean that it's foolproof, but one thing that you can do is if you want to just have some extra confirmation, go ahead and plug in the order pair that is part of the problem. If I can plug in that order pair, and if I can get both sides to equal to each other, then that kind of gives you that extra assurance that, okay, my algebra is correct, that I created something that is equivalent. So if I plug 3 in for y, if I plug 2 in for x, I'll get natural log of 1, which is 0. 0 plus 1/3 is 1/3. 1 over 1/3 is 3, and 3 equals 3. So I'm able to prove that that order pair lives on that equation. Okay, let's see if we can make some progress on page 17. Okay, so a large vat is initially filled with salt water solution, a solution with higher concentration. A solution with higher concentration of salt flows in the vat and solution flows out of the vat at the same rate. The number of pounds of salt in the vat at time t minutes is modeled by the function a that satisfies the differential equation. At time t equals 10 minutes, the vat contains 50 pounds of salt. Write an equation for the line tangent to the graph of a at t equals 10. So typically, when we do tangent equation, we use x's and y's, which is fine. We can go ahead and set it up that way, but then we have to adjust the variables in our problem, right? So instead of x, what variable are we working with here? T, yep. Instead of y, we're going to use what? A, yep. So let's go ahead and just make the adjustment so that we can have that in front of us. Okay, so what is our point? What point are we using here? What's our t comma a here? And 50. 10 and 50, yep. So we can use that order pair to find our derivative. Our derivative is dA dt. So the only thing dA dt needs is an a, which is going to be that 50. We can plug that 50 in to get our dA dt, our slope. Okay, we can build our tangent line equation from here, right? We have our order pair, we have our slope. Solve for A, and then we can plug in that decimal or plug in that 12 for our approximation. Okay, part B is a little bit of kind of algebraic. Kind of just a little bit of kind of rearranging to get where we want to be. So it says that show that A of t is equal to this, that satisfies the differential equation dA dt. So what we want to do is we want to basically find the derivative of this, and then from the derivative, see if we can rearrange it to eventually look like this. Okay. So let's think about the derivative, right? What's the derivative of 300? Just what? 0, right? And this is e to the u. What's the rule for e to the u? Yeah, e to the u times u prime. So that's the way that we're going to approach it, right? So 300 goes to 0. 250 is going to stay. E to the u becomes e to the u times u prime. The derivative of my exponent is just going to be negative 0.02 because that's going to be power rule for my exponent. And if I clean that up, I can make that look like 5e because negative 250 times negative 0.02 is 5. And then so it's 5e to the negative 0.2 minus 0.02. And then we kind of have look at our dA dt and say, okay, how can I get that to look like dA dt? And then I can play with dA dt and say, well, maybe I can't quite make this look like this, but maybe I can play with this to eventually get both sides to look the same. So then we know dA dt is it's minus 0.02. I know A is just my original equation. So if I replace A with that 300 minus 250, and if I distribute the negative 0.02 through and combine like terms, I can get both sides to match, and that's what I want. So it's kind of like doing proofs where you're working on both columns to get both sides to match to show that they're equivalent. Okay, so your homework up to page 18. All right, come get your phones. Yeah.